In section 9.5, we're going to be looking at different applications of differential equations. And the first example we're going to look at is that logistic model or a population model. So we're real familiar with this model, so why don't I just go ahead and give you what the general solution is for a logistic model. Okay? The general solution is going to be that the population at any time t is equal to k, and here k is that carrying capacity, which would be the stable equilibrium solution, over 1 plus k over p sub 0 is our initial population, okay, minus 1 times e to the negative rt. In example 1, we want to solve the logistic equation, and here we have r is 0.2, our carrying capacity k is 600, and our initial population is 100. And then we're going to go ahead and graph the solution. So this is simply a substitution. Our population at any time t is going to be 600 over 1 plus the 600 over 100 will turn into 6 minus 1 times e to the negative 0.2 t. And when we simplify this equation, the population at any time is going to be 600 over 1 plus 5 e to the negative 0.2 t. And then when we graph this solution, all we have to do is just plug it into a calculator. But let's say that you didn't have a calculator. And now since this is modeling a population, it'll turn out that the graph will be in the first quadrant. But again, let's just say that you weren't using a calculator. Well, we know our initial population is 100. So I'm just going to pretend like this is 100 here. And this is where my graph is going to start. Well, the carrying capacity is 600. And remember, that's a stable equilibrium solution, which means that my population, since the initial population starts below 600, it's going to have to approach the 600 and follow it. The carrying capacity is like a horizontal tangent line, right? Or a horizontal asymptote, sorry. So we could verify this without even plugging it in a calculator by just looking at the limit. As t goes to infinity, okay? Remember, this is our t-axis, and this would be the p-axis. So if we take the limit as t goes to infinity, remember e to the negative exponent will drop below to be the limit as t goes to infinity of 600 over 1 plus 5 over e to the positive 0.2t. And now since the denominator is going to keep growing and growing and growing, this fraction is going to approach 0. So the limit as t goes to infinity will just be 600, our carrying capacity. So we've gone through the logistic model quite a bit. I didn't want to derive the formula, I just wanted to give it to you. But what we're going to do on the next few pages is we're going to look at different models, and we're going to go ahead and derive specific solutions. So the next example is called the Gompertz growth model, and that's commonly used to model the growth of tumors in cancer patients. So in example 2, it says find the general solution, and we have that R is 0.5, K is 700, and our initial size of our tumor is 12. And typically when we're talking about the growth of tumors, we're talking about milliliters. So if there's no units, you can assume those units. Well, my general differential equation that's modeling the growth of the tumor, the growth rate of the tumor, is m prime of t. I know what my r is, so I'm going to substitute that in and get negative 0.5. I don't know what m is, that's what I'm trying to find. And then I have natural log of m, which I'm trying to find, over the carrying capacity of 700. Now this is a separable equation. If I divide both sides by m times the natural log of m over 700, then I can just take the derivative, or the integral, sorry, on both sides. All right. So I'm going to leave the constant negative 0.5 on the right-hand side, and then I'm going to integrate both sides to get 1 over, remember I'm using the property that it's separable, natural log, m times natural log of m over 700, and this would be with respect to m. On the right hand side, it's going to be with respect to the variable t. I'm going to skip some of the algebra steps just because of the space. Looking over at the left hand side, I'm going to do a u substitution on natural log. So I'm going to let u equal the natural log of m over 700, which means my du is going to be equal to, turns out, 1 over m dm. So again, you can just verify that. I'm going to be skipping steps because of space. And then our integral will be 1 over u du. Okay. On the left-hand side. And on the right-hand side, it's going to be negative 0.5t plus the constant c. One over u is the natural log of the absolute value of u, but why don't I just go ahead and substitute back in for u the natural log of m over 700, and that's in absolute values, equal to negative 0.5t plus c. If I exponentiate both sides, and I'm going to do this in one step, I'm going to take e to both sides, and I'm also going to get rid of the absolute value by putting a plus minus on the right hand side to get natural log of m over 700 is equal to plus or minus, this will turn into e to the c times e to the negative 0.5t. So again, you can just go ahead and verify that. Now what I'm going to do is I'm going to replace the plus minus e to the c. E to the c is a constant. Plus a constant minus a constant isn't going to change anything. So I'm just going to substitute all of that. I'm going to put in c. This becomes the natural log of m over 700. equal to some constant c, oops, this is supposed to be e, sorry, times e to the negative 0.5t. I want to get rid of the natural log on the left-hand side, so I'm going to exponentiate again to get m over 700 equal to e, exponent is c e to the negative 0.5t. And then multiplying both sides by 700, I finally have solved, and it's an ugly solution, for the mass of the tumor at any time, equaling 700 e raised to the c e to the negative 0.5t. We have some initial conditions. Remember, we have the initial mass is 12. So since the initial mass is equal to 12, what that means is that when t is equal to 0, the mass is equal to 12. And solving for the variable c, we'll have that c is equal to the natural log of 12 over 700. So 12 over 700 will reduce by 4. All right, we're almost there. So now we've found out what our C is, the size of our tumor, the mass of the tumor at any time t. It's going to be equal to 700. E to the C is natural log of, maybe I'll write this as 3 over 175 times e to the negative 0.5t. And then just playing around with some of the properties of logs, we can write this in a better way as 700 times 3 over 175, and the exponent on 3 over 175 is e to the negative 0.5t. So this is where I would stop, just to let you know that in a lot of your science courses, they don't like this notation where the exponent is actually the constant e. So oftentimes in your physics class or biology class, they will replace the exponential e with the exponential function notation exp of negative 0.5t. I actually don't care which one you use. So now what we want to do is, we found our general solution, okay, with those special conditions, but now I want to go ahead and graph this equation. So I'm looking at the first quadrant, where with respect to time we have the growth of some tumor. The initial size of our particular tumor is at 12, we can assume it's millimeters. As t goes to infinity, e to the negative 0.5t, what's going to happen is that's going to approach 0. So 3 over 175 to the 0 power is just 1. And this whole thing will approach the carrying capacity, K, of 700. So the graph will grow and then approach its carrying capacity. All right, so let's try another common problem that shows up in physics. And this is what we called call a stirred tank reaction. Something that we should review from physics is that when we have a mass, any mass of a fluid, it's going to equal the concentration times the volume. In our stirred tank problem, what we're looking at is a specific scenario where you have a mixture. Typically it'll be a saline mixture, or my example is a sugar solution where we have sugar and water, and you want to keep stirring the mixture because you don't want in my case, or my example, I'm looking at sugar water, you don't want the sugar to settle, right? You want it to have an even consistency. So it's constantly being stirred. And we're going to assume that the tank is filled to some volume V. As we are draining out the solution, we are flowing in a solution at the same rate. And this is important. It has to be at the same rate, or else the tank will not remain full. It'll either overflow or it will empty. So this is going to be the same rate. The amount going in and the amount coming out. So the volume will remain constant. Let's go ahead and look at the example first, and then we'll apply all these millions of variables to it. So let's say we have a 1,000-liter tank. So the 1,000 liters here means that this is V, this is our volume. And this tank is filled with a sugar solution that has an initial concentration of 5 grams per liter. A sugar solution of 25 grams per liter is going to flow into the tank. Okay? So that value is going to be this C sub I, which is the inflow of concentration. Now the rate that it's flowing in is 8 liters per second. And then the mixed solution is flowing out at a rate of 8 liters per second, which has to be the same, or else the tank will either overflow or empty. So this is our R, the inflow-outflow rate. Okay? So we're going to find the mass of sugar in the tank in part A. So R is 8. Well, let's just go ahead and look at our formula. The rate at which the mass or a fluid is changing, the mass of the sugar in our fluid is changing, is going to be a negative R over V. R is 8. And I'm going to leave off the units. I'll put them on at the end. V is the volume of the tank, which is 1,000. Okay. M is what we want to find, plus the C sub I is 25. And then R again is 8. When we clean this up a little bit, I have M prime. And I think I'm going to write this as a decimal, negative 0.008 m of t plus 200. So what I want to bring your attention to is the form of this equation. This is that special first order linear form that we had in 9.4, where the m prime would be your y prime of t, the negative 0.008 is k, times y of t, and the 200 is b. So it's the kb form. And I know what that solution is supposed to be. The solution is going to be m of t is equal to some constant c times e to the, in this case it's kt, and our k is negative, so negative 0.008 t minus, and then since our b is a plus and our k is negative, it's going to be minus minus or plus, and we'll have 200 over, or b over k. So 200 over the 0.008 should turn into 25,000. So now all I have to do is use that, our initial condition, which is the initial mass. Well, how do we figure out initial mass? Going all the way up to the top, mass is concentration times volume. And our initial concentration is the 5 grams per liter. Okay, so the initial amount of sugar in this tank is going to be the initial concentration of 5 times the volume, which was 1,000. So our initial mass is 5 times 1,000, or 5,000. Well, when we solve for our constant c, we'll have 5,000 is equal to c plus 25,000, which means the c is negative 20,000. So bringing all of this together, the mass of sugar in our tank at any time is going to equal to negative 20,000 e to the negative 0.008 t plus 25,000. This is the equation that we're looking for. Just to let you know that the units are in grams here for the mass. Now in part B, we're supposed to find the concentration of sugar in the tank for any t value. So I'm going to create this new function c, and that's going to stand for the concentration. But remember, if mass is concentration times volume, then concentration, let me bring this up. So the concentration is going to be equal to the mass divided by the volume. And again, I'm going to go ahead and call this function C for concentration. I already found my mass function from part A, which was negative 20,000 e to the negative 0.008 t plus 25,000. And now I'm going to take this mass and I'm going to divide it by the volume. The volume is constant in this particular problem, which is 1,000. When we simplify this equation, the concentration of sugar at any time is going to be equal to negative 20 e to the negative 0.008 t plus 25. And when we talk about concentration, concentration is grams per liter, so the amount of sugar in grams per liter of water in this case. Let's look at our last. The last example we're going to look at is what we call a predator-prey model, and that's actually where we're comparing two species, where one is the predator and the other is the prey. So I'm going to use F for predator and prey for H. And the reason why is because this is modeled after a famous fox and hare problem, where the foxes are the predators and the hare are the prey. And when we look at the rate at which the fox's population changes, it's going to depend on two things. One is the foxes are going to have a rate at which the population declines, which is why we have this negative A in front. That's the rate at which the population of the foxes decline, and then we're going to add it to this rate B at which the foxes eat the hares. And that will increase the population of the foxes. Now, when we look at our prey animals, our hare, and we look at the rate at which their population changes, typically hares or prey animals tend to reproduce very quickly. So their population grows fast. However, this minus here means I'm going to take away where hares and foxes meet, because that's where the fox eats the hare, and that's going to be at some rate at which the population of the hares will decline. In example 4, I'm just going to give you two generic equations, and you're going to have to choose which is the predator and which is the prey. So all you have to do is compare it to the above equations. If we look at x prime, we have a minus, plus, and then x times y. So that looks like the first equation, minus plus x times y. So x is the predator, and then y would have to be the prey, which makes sense because it's going to be positive, negative xy. Y is prey. Our goal here is to be able to graph a direction field modeling predator and prey. So the first thing we want to do is we want to figure out equilibrium solutions where these differential equations are equal to 0. So if I set each one of these equal to 0, the negative 3x plus 6xy, if I set that differential equation equal to 0, and I factor out the common negative 3x, that'll give me 1 minus 2y is equal to 0. So this is just basic algebra, right? We have an equation set equal to 0. We're going to factor and set each factor equal to 0. Gives me x is equal to 0, y is equal to 1/2. So let's look at the y prime. When we set y prime equal to 0, we have y minus 4xy equal to 0. Factor out the common y times 1 minus 4x equal to 0, and then set each factor equal to 0. I have y is equal to 0, x is equal to 1/4. Typically, we ignore the values when we're trying to find equilibrium points. We ignore the 0 values because that's actually where the population of the predator and the population of the prey are 0, which means nothing. We have nobody. So the equilibrium solutions are usually the non-zero solution. So y is equal to 1/2 and x is equal to 1/4 would be the equilibrium solutions. So the next part is to find the equilibrium points. what I'm going to do is I'm going to do a sketch of the first quadrant. And I'll call this X and Y. So let's say that this is 1/4, and here we have 1/2 on the Y. I'm going to go ahead and break up the first quadrant into fourths. Where these two lines intersect is going to be my equilibrium point for part C, which would be the point XY, so 1/4, 1/2. This is an equilibrium point. But notice that where X and Y are both 0, that's technically an equilibrium point as well. So I'm just going to list it, even though it's when the population is typically 0. Okay. And now what I'm going to do is I'm going to look at all the possible derivatives for each of these four pieces. Okay. So part C was to find the equilibrium points. This is going to be C. These are my equilibrium points. And that came from part B. Now I'm going to look at D. Oops, want it to be blue. In D it says identify the 4 regions in the first quadrant which are negative and positive. So here are my 4 regions in the first quadrant. Let's look at what happens with our derivative. So we're going to go back to B and look at the factored form of our derivative. Okay. Or maybe I should just write it down again so that you can compare that. Remember, the derivative with respect to our predator is going to be equal to negative 3x 1 minus 2y. And the derivative with respect to the prey is factored out of y, and we got 1 minus 4x. So I'm just looking at the factored form of those differential equations. Let's look at all the possible things that could happen. Well, what if both x and y are greater than, so let's say that x is greater than 1/4. So I'm looking at all these 4 regions, and y is greater than 1/2. Okay. So where x is greater than 1/4 and y is greater than 1/2, that would be in this region here. If we put values of x greater than 1/4 and values of y greater than 1/2, what happens is the derivative with respect to x is going to be greater than 0. So if you look at the derivative of x, if x is greater than 1/4, it's going to be a negative times a negative if y is greater than 1/2. Negative times negative is positive. However, if you put in values of x that are greater than 1/4 and values of y that are greater than 1/2, y prime is actually going to be negative. So if this is some random point in this region, think about vectors. I'm going to have positive movement in the x direction, but negative movement in the y. So if this is my starting point, I'm going in this direction, downward, right, and to the right. All right, let's look at another scenario. Let's just say that x is still greater than 1/4, but suppose that the y values are between 0 and 1/2. How does that affect our derivative? Well, it turns out that the derivative with respect will now be negative, and the derivative with respect to y will also be negative. So we'll pick some point where the x's are greater than 1/4, but the y's are between 0 and 1/2. And we'll note that the x value is negative, which means we're going to go to the left, and the y value is negative, which means we're going to go down and draw a vector. So that would be the direction of the vectors in that region. Okay, the other scenario is if the x values are between 0 and 1/4. So if x is between 0 and 1/4 and y is greater than 1/2, we're going to be here. And in that case, the derivative of x is positive and the derivative of y is positive. So that means x positive, y positive, draw a vector. Last case would be x between 0 and 1/4 and y between 0 and 1/2. In that case, derivative of x is negative and y is positive. So we have some random point. We're going to go to the left and up and draw ourselves a little vector. And I'm only doing this to notice the direction that my solution curves will be generated in. What's going to happen is that it'll evolve clockwise. So we've identified the 4 regions and where our derivatives are negative and positive. We're going to go ahead and look at part E. And this is the sad one because I'm horrible at drawing predator-prey direction fields. And in this case, our direction fields, you can make them look like little arrows if you wish. I'll show you what I mean. So let's go ahead, and maybe I want to keep that quadrant up there so I can kind of see it. Let's go ahead and draw first quadrant. No, I need space. Where we have x and y. Say this is 1/4, but here we'll call this 1/2. And we have this equilibrium point. Okay. So remember that everything was being generated clockwise, right? So we had a clockwise by the previous region graph. We had clockwise, we're going to call it an evolution. So the motion is clockwise. So that means direction here would be little direction arrows. We're going to look at little vectors. Okay. We're going clockwise. So if we look at these as being little vectors, okay, we're going to just look at the same way we did with direction fields, except for at some point here we have to make corners. Okay? And I am not real good at drawing these, to tell you the truth. So you can put arrows on them if you wish, or you don't have to. I just do little arrows because there is a direction in which it's generated. Okay. And we're just going to keep moving these around till it looks kind of like this. So that would be the sketch of a solution curve with little arrows, but you don't need the arrows. If we wanted to identify a particular curve, we just follow our arrows and note that it's being generated in a clockwise direction or a clockwise evolution. All right, so that's it for 9.5.